that time the initial momentum is equal to zero because nothing is moving. Both the entities were inside the gun. That means the gun plus the bullet, everything was inside the gun, internal matter. Now the trigger is made on, and something takes place inside the gun, and that also inside the gun, no external force is acting, and the bullet is going out with a certain velocity. At that time, the gun will move in the opposite direction. So initially there was no momentum, but finally some momentum takes place, right? So in this case, initial momentum was equal to zero, and the final momentum is something, right? So, but both must be equal. That means M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. But M1 U1 plus M2 U2 is equal to zero. So in this case, suppose the mass of the bullet is equal to small m, and the mass of the gun is equal to capital M. The velocity with which the bullet is moving is small v, and the velocity with which the gun is jerking backward is capital V. Then we can write initial momentum, total initial momentum is equal to total initial momentum is equal to total final momentum. Total initial momentum is equal to zero. That is equal to total final momentum. Total final momentum is equal to what? Momentum of the bullet plus moment of the gun first. Moment of the gun first. That is equal to capital M, capital V plus moment of the bullet means small m and small v we can write. Initial momentum is equal to zero because initially the bullet and the gun was at rest, right? There was no motion, hence there was no momentum. Initial momentum was zero. Once the bullet is fired, then both will get velocity. Bullet moves with the bullet of mass small moves the velocity small v, and the gun of mass capital moves the velocity capital V. Am I correct? So this is the condition. Therefore, capital M V is equal to small m small v. Therefore, capital V is equal to small m small v divided by capital M. Right? This negative sign shows that the gun is recoiling. Recoil velocity of the gun can be calculated using which theory? Conservation of linear momentum. Right? Conservation of linear momentum. Another thing is that this is impulse momentum theorem. Impulse momentum theorem. Impulse momentum theorem is suppose when a gun is operated. So in warfield and all, a gun is operated and if the soldier is firing and in a time small t seconds, so many bullets are going out. So many bullets of the same mass are going out with velocity v. Each bullet has a momentum is equal to small m into small v. Suppose n bullets are going out of the barrel toward the enemy, right? And therefore the total momentum is equal to n into m into v, right? So the jerk taking place will be minus m into n into m into v, right? Jerk is what is called, this is an impulse only, because in this case the large force is acting on your body for a very short interval of time, right? So the effect of the force is called impulse. The backward force, what is called impulse, that is F into T. In time T seconds, the impulse acting on the operator, the gun operator, in time T is equal to F into T. F into T is due to the change in momentum of the bullets as a whole. That is minus N M V. Minus sign means because the backward force, that means we have to apply a force on the gun to keep it intact at the same position itself. That is a change in momentum in the opposite direction. That is Ft is equal to minus Nmv. So this is a very important theorem. This theorem is what is called impulse momentum theorem. What is called impulse momentum theorem. Impulse momentum theorem. Impulse momentum theorem means F into T is equal to minus N. That means N is the number of bullets coming out of the gun in T seconds. In T seconds. And MV is the momentum produced in a single bullet. In T seconds, N bullets are going out. Therefore, the force or change in the total change in momentum is equal to NMV. So to keep the the gun intact in the same position itself. An opposite force that has applied on the gun is equal to minus n, n mv, because this force are acting in a very short duration of time. Therefore, ft is the impulse. So this theorem, ft is equal to minus n, small m, small v. This theorem is called impulse momentum theorem, right? So next thing what I want to tell you is a very simple thing. That is what is called rocket propulsion. So nowadays the rocket is projected into the air with multi-stage rocket. It is called multi-stage rocket. Means there are so many stages in a rocket, right? First of all, first part, the initial part, the starting part is ignited. That part contains it is a fuel chamber only. That fuel chamber, when burns, it produces gas, and the gas will be coming out through a small hole through a very high speed. That is called action, due to which the rocket is moving upwards. Once the fuel in that chamber is completely finished, that part will be detached. Mass is getting changed, and also due to the loss of mass. That means when any chamber is fired, gas is coming out. That means the rate of loss of mass is taking place at every moment. Due to change in mass of the body, the velocity can change. So this rocket propulsion basically that works on the principle of linear conservation of momentum. So the application of linear conservation of momentum, when we talk about, the first thing that comes in my mind is rocket propulsion. So when the rocket is not fired, its mass is equal to m0. M0 is what you call the rest mass of the rocket, right? The rest mass of the rocket is rest mass. Rest mass of the rocket. A rocket ROCK, rocket is equal to M0. Now the rocket is fired. Means every instant a certain amount of gas is coming out, due to which the mass will be getting reduced every time. The rate of loss of mass is equal to delta m by delta t. Rate of loss of mass. Rate of loss of mass is equal to delta m by delta t. In a small duration of time, suppose the delta m amount of gas is coming out, due to which there is a change in mass. So rate of loss of mass means loss of mass per unit time is equal to delta m by delta. Suppose at time t seconds, when you open your eye, t time has already passed after firing the rocket. Then what is the total loss of mass? So loss of mass in time t seconds is equal to delta m by delta t into t I can write. So when you look at the rocket, what is the mass then? So at any time, mass capital M is equal to m0 minus delta m by delta t into t we can write. This is the mass at any instant of time, right? Suppose that at this stage, when you look at the rocket in its process, at any instant, its mass is m. M is equal to delta m by delta. So m0 minus delta m by delta t into t. What is delta m delta t into t? In t time already passed. How much mass already lost? This much amount of loss already, a mass already lost. Therefore, what is the mass now? M. M is equal to whole mass minus the mass lost in t seconds. Now we suppose that at this stage, a small amount of mass is also ejected through the small hole, right? Due to firing, small mass is delta m. Suppose that delta m is passing out with the velocity u, right? Due to that loss of mass delta m, the main mass is not reduced much, because the total mass remaining in the system is very much greater as compared to loss of mass delta m. Suppose that in this stage, when mass m is m0 minus delta m by delta t into t mass is there at that instant, suppose a small amount of mass delta m is again ejected out as gas with the velocity u, due to which this main mass is moving with the velocity delta v. Right? Then we can write, by conservation of linear momentum, we can write m0 minus delta